Earth is not the best planet in the universe. That statement, sitting quietly in the air, carries the weight of an entire paradigm collapsing. For all of human history, every religion, every philosophy, every civilization that ever looked at the night sky and wondered, Earth has occupied a special position, not just in theology, in science, in the very framework through which we search for life beyond our world. Earth has been the standard, the template, the reference point against which every other candidate world is measured. And then the Kepler Space Telescope looked at the sky. What it found did not merely expand the catalogue of known worlds, it dismantled the assumption that Earth represents some kind of cosmic ideal, that life, if it exists elsewhere, would need to find conditions resembling our own. The data that flowed back from Kepler across its 9.5 years of operation pointed towards something the scientific community was not fully prepared to accept: worlds that score higher than Earth on every metric we use to assess habitability. Worlds with more stable energy sources, worlds with older suns, worlds with more clement temperatures, worlds by any rigorous calculation more suited to the emergence and persistence of complex life than the one we were born on. These worlds have a name: superhabitable planets, and they are real. They are confirmed, and what they imply about our place in the cosmos is something we are only beginning to fully reckon with. But before we begin, if space fascinates you, a like and subscribe means everything to us. Let's begin. To understand how Kepler found worlds better than Earth, we need to go back to the question that launched the mission in the first place. A question so fundamental it sounds almost naive. Are there other planets out there? Before 1995, that question had no confirmed answer. Planets around other stars, exoplanets, were theorized, debated, hoped for, and searched for across decades of astronomical effort. The technical obstacles were formidable. A planet does not produce its own light. It reflects light from its host star, and the ratio of that reflected light to the star's own luminosity is so vanishingly small that detecting it directly, from light years away, was for most of observational history simply impossible. The first confirmed detection of planets around another star did not come from direct imaging. It came from an entirely different method. In 1992, astronomers Alexander Wolszczan and Dale Frail detected planets orbiting a pulsar, a rapidly spinning neutron star. Through the slight variations the planet's gravity induced in the pulsar's precise timing signal, these were not the life-friendly environments anyone had imagined. Planets orbiting the corpse of an exploded star, bathed in intense radiation. Remarkable discoveries, but not candidates for habitability. Then, in October 1995, Michel Mayor and Didier Queloz at the Geneva Observatory announced the detection of 51 Pegasi b, a planet approximately half the mass of Jupiter, orbiting a Sun-like star once every 4 days. It was detected via the radial velocity method, measuring the tiny Doppler wobble in the host star's spectral lines induced by the gravitational tug of the orbiting planet. A discovery so significant that Mayor and Queloz were awarded the Nobel Prize in Physics in 2019. But 51 Pegasi b was a gas giant, orbiting so close to its star that its surface temperature approached 1,000 degrees Celsius. Not habitable, not even close. What the astronomical community needed, what decades of philosophical speculation and scientific searching demanded, was a systematic survey. Not the one-at-a-time detection of individual planets through ground-based radial velocity measurements, but a comprehensive census. A mission designed from the beginning to answer a specific audacious question: what fraction of Sun-like stars host Earth-sized planets in their habitable zones? That mission was Kepler, named after the 17th century German mathematician and astronomer Johannes Kepler, whose laws of planetary motion remain foundational to orbital mechanics to this day. The Kepler Space Telescope was launched on March 7, 2009, aboard a Delta II rocket from Cape Canaveral, Florida. It entered a heliocentric orbit trailing behind Earth, positioned to avoid Earth's shadow, while maintaining a stable thermal environment for its extraordinarily sensitive instruments. The telescope's primary instrument was a photometer, a device measuring the brightness of stars with exceptional precision. Kepler stared at a single patch of sky, centered on the constellations Cygnus and Lyra, containing approximately 150,000 target stars simultaneously. It monitored the brightness of each star continuously, measuring fluctuations at the level of parts per million, detecting changes in stellar luminosity. The transit too small for any previous instrument. When a planet passes between its host star and our line of sight, it blocks a tiny fraction of the star's light. For an Earth-sized planet transiting a Sun-like star, the brightness dip is approximately 84 parts per million, roughly 0.0084%. Barely measurable, but measurable. For Kepler, operating above the blurring effects of Earth's atmosphere, with its 0.95-meter aperture and 42 charge-coupled device detectors covering a 115 square degree field of view, it was detectable with extraordinary reliability. Over 9.5 years of operation, with a brief hardware interruption in 2013 that led to the repurposed K2 mission, extending its science life until final retirement in October 2018, Kepler observed more than 530,000 stars and confirmed the existence of 2,662 exoplanets. Its candidate list, including unconfirmed detections, stretches beyond 4,000 objects. The statistical implications of these numbers, extrapolated to the full stellar population of the Milky Way, suggest that our galaxy contains somewhere in the range of 300 billion planets, roughly one for every star, possibly more. The sheer scale of that number tends to numb the mind rather than illuminate it. So let us ground it differently. If you were to spend 1 second examining each planet in the Milky Way, it would take you longer than the current age of the universe to finish. There are more planets in our galaxy alone than there are seconds in the history of time since the Big Bang. But raw numbers were only the beginning of Kepler's revelations. Among the thousands of confirmed exoplanets in Kepler's catalogue, a specific subset attracted the closest scientific scrutiny: rocky, terrestrial planets with radii between 0.5 and 2 Earth radii, orbiting within the habitable zones of their host stars, the range of orbital distances at which liquid water could theoretically exist on a planetary surface. This is the classical habitable zone definition, formalised by James Casting and colleagues in a 1993 paper that remains one of the most influential works in astrobiology. Within Kepler's habitable zone, rocky planet candidates, scientists began identifying objects that were not merely Earth-like. They were, by certain quantitative measures, better than Earth, more promising, more capable of supporting not just life, but complex, persistent, potentially long-lived life, the kind of life that might, over billions of years of evolution, develop the complexity we associate with intelligence. This concept needed a name, and in 2014, it got one. Dirk Schulze-Makuch, a planetary scientist at the Technical University of Berlin, along with René Heller at the Max Planck Institute for Solar System Research, published a paper in the journal Astrobiology introducing the concept of the Earth Similarity Index, or ESI, and more provocatively, the concept of superhabitable worlds. The paper laid out a systematic framework for evaluating not just whether a world could host life, but whether it could host more life, more complex life, more persistent life than Earth currently does. Their framework challenged an assumption that had been embedded, largely unexamined, in the architecture of every exoplanet search conducted to that point. The assumption that Earth is optimal, that the conditions on our world, the mass, the orbital distance, the stellar type of our host star, the age of our system, represent some kind of Goldilocks ideal, that the best planet for life is a planet most similar to Earth. That assumption, Schulze-Makuch and Heller argued with careful quantitative rigour, is not justified by biology, geology, or planetary science. It is a form of selection bias, the assumption of optimality by the only example we have direct access to. It is, in a meaningful sense, a cosmic version of thinking your hometown is the best place on Earth simply because you were born there. The data from Kepler said otherwise, but that is not the full story. Because the concept of superhabitable worlds does not just rearrange our ranking of individual planets. It forces a fundamental reconsideration of where in the universe life is most likely to exist, when in cosmic history it is most likely to emerge, and whether the emergence of intelligent spacefaring life on Earth represents a typical outcome or a remarkably premature one. The Earth Similarity Index begins with a question that sounds straightforward, but proves remarkably difficult to answer rigorously. what makes a planet good for life? The naive answer is, make it like Earth. But this assumes the conclusion. What we need is a bottom-up analysis, starting not from Earth's specific parameters, but from the underlying physical and biological requirements for the emergence, persistence, and complexity of life. What does life actually need? At its most fundamental level, drawing on the one example of life we have direct access to, life requires liquid water, a source of chemical energy, a stable environment over relevant timescales, and the raw materials for organic chemistry, primarily carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Beyond these absolute requirements, the richness and longevity of a biosphere seems to depend on additional factors: the diversity and cycling of chemical environments, the stability of climate, the availability of energy, and the duration of hospitable conditions. When Schulze, McCouch, and Heller systematically worked through these requirements, they found that several of Earth's specific characteristics sit at non-optimal values for at least some of them. Earth is not the worst possible world for life, but neither is it the best. Let us work through the major criteria. Mass and gravity first. Earth's mass is approximately 5.97 times 10 to the 24th power kilograms, and its surface gravity is 9.8 meters per second squared. These are the numbers all other candidates are measured against, but are they optimal? Life benefits from planetary mass in several ways. A more massive planet retains a thicker atmosphere, providing better radiation shielding, greater air pressure to keep water liquid across a wider temperature range, and a more active geological interior. Internal geology, specifically plate tectonics, driven by heat from the planet's interior, is increasingly recognized as a critical factor in long-term habitability. Plate tectonics cycles carbon between the atmosphere and the crust through subduction zones, regulating atmospheric CO2 concentrations over geological timescales, and thereby stabilizing climate against the long-term brightening of the host star. Without plate tectonics, a planet may lose its capacity for this carbon silicate cycle, eventually either freezing over or running away into a Venus-like hothouse state. A planet roughly 1.5 to 2 times Earth's mass, a super-Earth in the parlance of exoplanet science, retains more internal heat over longer timescales, potentially sustaining plate tectonics for billions of additional years beyond what Earth will manage. It also holds a thicker atmosphere with greater pressure, keeping water liquid across a wider range of temperatures, and its stronger gravity moderates atmospheric loss over geological time, maintaining a more stable chemical environment for biology. By this analysis, a planet of approximately 1.5 Earth masses is not just adequate for life, it is superior for life. Better geology, better atmospheric stability, better long-term climate regulation, a more enduring habitat. Now here is where it gets truly strange. Kepler's catalogue contains hundreds of candidates in exactly this mass range. Rocky super-Earths, between 1.2 and 1.8 Earth radii, corresponding roughly to 1.5 to 3.5 Earth masses, are among the most common planet types in the galaxy. More common than Earth-sized planets, more common than gas giants. The most typical planet type that nature produces, it appears, is the one our solar system conspicuously lacks, and it is, by the metrics of superhabitability, the one most likely to produce rich, long-lasting biospheres. Our solar system's failure to produce a super-Earth is, from a statistical standpoint, unusual. Most planetary systems that Kepler observed contain at least one planet in this size range. The absence of such a planet in our own system may, in fact, be a meaningful data point about why we find ourselves on Earth, rather than somewhere better suited for our kind of complexity. This is a concept we will return to, but it requires patience, because it touches on some of the deepest questions in all of science. Temperature next. Earth's average global surface temperature is approximately 14 degrees Celsius, 287 Kelvin. This is comfortably within the range at which liquid water is stable, and biology as we know it can function. But is it optimal? Here the biology becomes instructive. On Earth, the richest ecosystems in terms of species diversity, biomass density, and biological complexity are not in temperate regions, they are in the tropics. Tropical rainforests occupy roughly 6% of Earth's land surface, but harbour an estimated 50% of all species. Tropical coral reefs, occupying less than 1% of the ocean floor, contain perhaps 25% of all marine species. Biodiversity, ecosystem richness, and biological complexity on Earth correlate strongly with temperature. Warmer regions, within limits, support more life. Optimal mean temperature for maximizing biological diversity on a planetary scale, based on extrapolation from these patterns, appears to be somewhere between 25 and 30 degrees Celsius, significantly warmer than Earth's current average. A superhabitable planet, by this analysis, would run slightly warmer than Earth. Not uncomfortably so, not a hothouse, but warmer, more tropical, more uniformly favourable to the kind of biochemical reaction rates and ecosystem productivity that support complex biological networks. Water distribution matters too. Earth's surface is approximately 71% water, but that water is distributed in a pattern that creates enormous dry land masses separated by vast ocean basins. The interior of large continents tends to be arid, distant from the moderating influence of the ocean, subject to extreme temperature swings between seasons. A superhabitable planet, some models suggest, would benefit from a more even distribution of shallow seas and smaller land masses, an archipelago world perhaps, or a world with no large continents at all. The result would be a more uniformly humid, more consistently temperate environment across a larger fraction of the planetary surface, more habitable area, more biological diversity, more ecological complexity. Let us pause for a moment and consider what this really means. If a planet with a mean temperature of 27 degrees Celsius, a mass of 1.5 Earths, and a surface distributed in shallow seas and island chains would systematically support greater biological richness than our own world, then Earth is not the ideal habitat. It is a functional one that worked well enough to produce us, but not the best the universe can do, not even close. The stellar host adds another layer to this analysis. Our Sun is a G-type main sequence star, a yellow dwarf with a surface temperature of approximately 5,778 degrees Kelvin and a main sequence lifespan of approximately 10 billion years. It is currently about 4.6 billion years into that lifespan. From a habitability standpoint, the Sun's characteristics are adequate, but not optimal. K-type stars, orange dwarfs, slightly cooler and less luminous than the Sun, with surface temperatures ranging from roughly 3,900 to 5,300 degrees Kelvin, outperform G-type stars on nearly every metric relevant to planetary habitability. Consider the numbers. A K-type star with 70 to 80% of the Sun's mass will remain on the main sequence, the stable, hydrogen-burning phase of stellar evolution, for 20 to 50 billion years. The Sun will remain on the main sequence for approximately 5 billion more years before swelling into a red giant and rendering Earth uninhabitable. A planet orbiting a K-type star has 2 to 5 times more time for the processes of biological evolution to operate. On Earth, complex multicellular life has only existed for approximately 600 million years, roughly 600 million years of the 4.6 billion year planetary age. Intelligence has emerged in only the last few million years of that. The arc from single-celled organisms to technological civilization required the better part of 4 billion years and a very specific sequence of evolutionary transitions, many of which appear in retrospect to have been unlikely. The more time a planet has, the longer its star burns stably, the more opportunities for those transitions to occur. A planet orbiting a K-type star in its habitable zone gets more time, more chances, more rolls of the evolutionary dice. K-type stars also produce less harmful ultraviolet radiation than G-type stars. UV radiation is a double-edged factor in planetary habitability. In small amounts, it drives chemical reactions that may be important for the synthesis of organic molecules, potentially including the precursor chemistry for life's origin. In large amounts, it damages DNA, disrupts protein function, and creates a hostile surface environment that biology must expend significant energy shielding against. K-type stars emit less UV than G-type stars, providing a more favourable radiation environment for surface life across a wider range of orbital distances. And K-type stars are far more common than G-type stars. They represent approximately 13% of all stars in the Milky Way, compared to roughly 7% for G-type stars. A universe more generous with K-type stars than G-type stars is a universe that, by the logic of superhabitability, provides better habitats more often. This is what Kepler found. Across its field of view, cataloguing planets around every stellar type in its sample, the data showed that K-type stars harbour rocky planets in their habitable zones at rates comparable to or exceeding those around G-type stars. The superhabitable zone around a K-type star, the orbital distance range where conditions are optimal by the criteria we have been discussing, is narrower than around a G-type star, but it is there, and planets have been found in it. Among the Kepler candidates, Schulze-Makusch and Heller and subsequent researchers identified 24 exoplanets meeting the criteria for superhabitability, older than Earth, orbiting more stable stars, potentially warmer, potentially more massive. Not all 24 are confirmed with certainty, but their existence in the Kepler data is not speculative. It is statistical. It is real. Let us name a few of them. Kepler 442b sits approximately 1,194 light-years from Earth in the constellation Lyra. It orbits a K-type star, cooler and more stable than our Sun, at an orbital period of approximately 112 days. Its radius is estimated at roughly 1.34 times that of Earth. Its equilibrium temperature, factoring in the stellar flux it receives, places it within the conservative habitable zone. Its Earth Similarity Index score is approximately 0.84, making it one of the highest-ranked Earth analogues in the confirmed exoplanet catalogue. By multiple measures of superhabitability, mass, stellar type, stellar age, estimated temperature, it scores better than Earth. And here is the profound implication. Kepler, 442b's host star, is older than the Sun. Older by enough that, if life emerged on Kepler 442b at roughly the same time after its star's formation as life emerged on Earth, that life has had more time to evolve, more time to develop complexity, more time to develop potentially intelligence. Kepler 1126b, Kepler 62f, Kepler 452b, announced in 2015 and briefly dubbed Earth's cousin by NASA, orbiting a G-type star slightly older and slightly dimmer than our Sun, at an orbital period of 385 days, with a radius approximately 60% larger than Earth's. Kepler 452b's host star is approximately 6 billion years old, 1.5 billion years older than the Sun. If life exists on Kepler 452b, it has had 1.5 billion additional years of evolutionary opportunity compared to life on Earth. What does 1.5 billion years of extra evolution look like? On Earth, 1.5 billion years ago, the most complex organisms on the planet were colonial algae. There were no animals, no plants, no fungi. Multicellular life was a recent innovation, just beginning to explore its possibilities. In 1.5 billion years of additional evolution from that baseline, Earth produced every multicellular organism that has ever lived. Every fish, every insect, every dinosaur, every mammal, every human being, and every biological innovation of the next billion years to come. If a world like Kepler 452b has had that head start, the complexity of any life there is not analogous to life on Earth today. It is analogous to life that will exist on Earth 1.5 billion years from now. We cannot currently imagine what that looks like, and that, in itself, is worth sitting with. The implications of this discovery are almost too vast to comprehend, but they point toward a conclusion that is simultaneously humbling and extraordinary. Earth is not the apex of habitable worlds. It is a beginning, a starting point in a universe that is capable of producing far richer, far longer-lived, far more complex biospheres than our own. All of this, the stellar optimization, the mass criteria, the temperature considerations, the orbital parameters, feeds into a central question that the superhabitability framework was always building toward. Is Earth special, or are we simply here? This is not a philosophical question dressed in scientific language. It is a direct empirical question, and the data from Kepler is beginning to provide direct empirical input toward its answer. To understand that input fully, we need to engage with one of the most important and contested ideas in all of science, the concept of rare Earth versus a habitable universe. In 2000, paleontologist Peter Ward and astronomer Joe Kirschvink, in a book whose thesis generated immediate and lasting controversy, argued that the emergence of complex multicellular life on Earth was not the inevitable result of common cosmic conditions. It was, they contended, the product of an extraordinarily unlikely combination of factors. A planet of exactly the right mass, orbiting a star of exactly the right type, at exactly the right distance, protected by a giant outer planet from excess asteroid bombardment, stabilized by an unusually large moon against axial wobble, positioned in the right region of the right kind of galaxy, appearing at the right moment in cosmic history. Remove any one of these factors, Warden-Kirschvink argued, and complex life fails. Earth is, by this account, vanishingly rare. The rare Earth hypothesis was influential and troubling in equal measure. If it were correct, the implications for the search for extraterrestrial intelligence were devastating. Not just that we have not found anyone, but that there is almost certainly no one to find. Kepler's data has not disproven the rare Earth hypothesis outright, but it has significantly complicated it. The hypothesis depends critically on the claim that Earth's specific combination of characteristics is extraordinarily unusual. But if superhabitable worlds with better combinations of the relevant parameters, are common in the galaxy, then the question shifts. It is no longer, is Earth rare? It becomes, why did complex life emerge first on a non-optimal world rather than on one of the many better candidates? And that question has an answer that is, in its own way, as profound as the rare Earth hypothesis itself. Consider the age distribution of potentially habitable worlds in the Milky Way. The Milky Way is approximately 13.6 billion years old. Star formation in the galaxy began early, within the first billion years, though it has proceeded at varying rates over the galaxy's history. Current astrophysical models of galactic chemical evolution suggest that the heavy elements necessary for rocky planet formation, particularly silicon, oxygen, magnesium and iron, did not become sufficiently abundant throughout the galaxy until roughly 9 to 10 billion years ago, as successive generations of massive stars cycled through their lives and seeded the interstellar medium with processed material. This means rocky, potentially habitable planets began forming in earnest, with sufficiently high metallicity to support complex geochemistry, approximately 9 to 10 billion years ago. The solar system formed 4.6 billion years ago, roughly 4 to 5 billion years into the epoch of rocky planet formation. Earth itself has only had life of any kind for approximately 3.8 billion years, and complex multicellular life for only about 600 million years. Against this timeline, Earth is not old, it is middle-aged. Younger than the majority of rocky planets currently circling older, more stable K-type stars throughout the galaxy. Planets that formed 8 or 9 billion years ago around stable K-type stars, assuming they developed life on timescales comparable to Earth, have had several billion additional years for biological evolution to operate. They are not our contemporaries, they are our cosmic elders. And if we think carefully about what this implies for the distribution of intelligence in the galaxy, the picture becomes vertiginous. If intelligence is possible on superhabitable worlds orbiting K-type stars, and we have no scientific reason to think it is not, then some of those civilizations are not millions of years ahead of us. They are billions of years ahead. Not more developed than us in the way that ancient Rome was more developed than Bronze Age villages. More developed than us in the way that we are more developed than the single-celled organisms that first emerged in Earth's early oceans. We cannot conceptualize what a civilization billions of years in advance of our own looks like. Our entire recorded history spans roughly 5,000 years. We have had radio technology for approximately 130 years, spaceflight for about 70. We are, in the timeline of any sufficiently old civilization in the galaxy, less than an eye blink into the period of technological capability. Some might wonder whether this comparison is fair, whether biology and intelligence are universal enough phenomena to allow meaningful comparisons across such vast timescales and radically different planetary environments. It is a legitimate caveat. We do not know that intelligence is inevitable, given sufficient time and a hospitable planet. We have one data point. On that data point, it emerged after approximately 4 billion years of biological evolution, but it required a specific and seemingly contingent sequence of evolutionary transitions, mass extinctions, and ecological reorganizations. Perhaps intelligence is common. Perhaps it is extraordinarily rare even given billions of years of opportunity. But this uncertainty cuts both ways. If intelligence is not rare, then the galaxy is teeming with civilizations far older than ours, and the silence of the cosmos is a problem that demands explanation. The Fermi paradox in its most acute form. If intelligence is rare, then even superhabitable worlds may be biologically rich but cognitively empty. Vast, complex biospheres without observers, beautiful, profound, but silent. Neither possibility is comfortable, but both are grounded now in real data. Kepler gave us the planets give us the paradox at full force. Let us return to the specifics. Because the question of what Kepler actually found, quantitatively, not just conceptually, deserves precise treatment. Among the 24 superhabitable planet candidates identified by Schulze, Makusch and Heller in their landmark 2020 paper, published in the journal Astrobiology, using criteria synthesizing stellar type, stellar age, planet size, planet temperature, and substrate conditions, none score higher than Earth on all criteria simultaneously, but several score higher on the majority of criteria considered individually. The most compelling candidate from this analysis is KOI 5715.01, a Kepler object of interest, a planet candidate that has not yet achieved formal confirmed status, but whose transit signals are considered reliable. It orbits a K-type star approximately 3,000 light-years from Earth. Its estimated radius is approximately 1.8 Earth radii. Its host star is estimated at roughly 5.5 billion years old, slightly older than the Sun. Its equilibrium temperature estimate places it within the optimistic habitable zone boundary. It receives approximately 1.07 times Earth's stellar flux from its host. By the composite superhabitability score developed by Schulze, Makusch and Heller, KOI 5715.01 ranks as the most superhabitable candidate in the Kepler dataset, 3,000 light-years away, roughly 1.8 times Earth's radius, orbiting a cooler, more stable star, older system, more time. These are not features of a world less suited to life than Earth. They are features of a world potentially more suited to life than Earth, and it was found because a space telescope stared at a patch of sky in Cygnus for nearly a decade and counted the shadows of passing worlds. The detection methodology matters here for an important reason. It tells us something about the limits of what we know. The transit method, Kepler's primary detection technique, is not uniformly sensitive across planetary parameters. It preferentially detects large planets on short orbital periods around nearby stars. A planet the size of Earth orbiting a Sun-like star at Earth's orbital distance produces a transit signal that, even for Kepler, requires multiple confirmed transit events to characterize reliably. Planets on orbital periods longer than a few hundred days are detected less efficiently, because fewer transit events occur within the observing window. This means Kepler's catalogue is not an unbiased sample of the true distribution of planets in the galaxy. It is a detection efficiency-weighted subset of that distribution, and the detection efficiency biases systematically underrepresent certain types of planets, specifically planets in longer period orbits around older, cooler stars, precisely the types of planets most likely to be superhabitable. The true number of superhabitable worlds in the galaxy, correcting for these detection biases, is almost certainly larger than the 24 candidates identified from the Kepler data. Potentially much larger. Statistical analyses published in the years following Kepler's primary mission, extrapolating occurrence rates from the detected population to the full stellar population of the Milky Way, suggest that tens of billions of rocky planets occupy the habitable zones of K-type stars alone. Tens of billions. Even if only a fraction of those meet the full criteria for superhabitability, the right mass, the right temperature, the right stellar age, the right substrate conditions, the number of superhabitable worlds in the Milky Way is likely to be measured in the billions. Billions of worlds, each potentially more suited to the emergence and persistence of life than the planet on which all of human civilization has ever existed, and we are only now beginning to find them. The James Webb Space Telescope, operational since 2022, with its 6.5-meter gold-plated mirror and infrared sensitivity that surpasses Kepler's capabilities by orders of magnitude, is beginning the work of characterizing these worlds in detail. Where Kepler could detect planets and estimate their sizes, JWST can analyze the transmission spectra of planetary atmospheres, measuring the wavelengths of starlight filtered through a planet's atmosphere as it transits, identifying the chemical fingerprints of atmospheric gases. In 2023, JWST provided transmission spectroscopy data for TRAPPIST-1c, one of the rocky planets orbiting the ultra-cool red dwarf star TRAPPIST-1, 39 light-years from Earth. The results constrained the carbon dioxide abundance in TRAPPIST-1c's atmosphere, providing the first direct atmospheric characterization of a rocky planet in another star system. The data suggested a thin atmosphere, possibly less hospitable than initially hoped for this particular world. But the methodology worked. The instrument demonstrated that rocky planet atmospheres are within its reach. The characterization of larger, more massive rocky planets, superhabitable candidates, is within JWST's capability in principle, particularly for those orbiting nearby K-type stars. The signal is stronger for larger planets. The atmospheric cross-section is greater. The transmission spectroscopy is more sensitive. JWST is looking, and what it finds in the atmospheres of the best candidates, oxygen, water vapor, methane, carbon dioxide in specific ratios, will determine whether the superhabitable worlds Kepler found are not just physically superior to Earth, whether they are inhabited. And that is a word that carries quietly the weight of everything. But this raises an even bigger question, one that the superhabitability framework by its own logic cannot avoid. If superhabitable worlds are common, if the galaxy contains billions of worlds more suited to life than Earth, and if those worlds have had more time for biological evolution to operate, then why are we here, on this non-optimal world, asking these questions? Why did intelligence emerge on Earth, with its G-type host star, its modest 4.6 billion-year age, its non-superhabitable mass, rather than on one of the better candidates? There are several answers. Each one illuminates something different about the relationship between planetary environments and the emergence of complexity. The first answer is the simplest and most humbling. We are here because we evolved here. The question of why intelligence appeared on Earth rather than on a superhabitable world assumes that intelligence has not appeared on superhabitable worlds. We have no evidence either way. The absence of detected extraterrestrial signals is not proof of absence, it is proof of non-detection. And non-detection, given our limited search coverage and the vast distances involved, is essentially uninformative. It is entirely possible, indeed, by the logic of superhabitability plausible, that the galaxy's superhabitable worlds are thriving biospheres, that some of them have produced intelligence, that some of those intelligences have developed technology, and that we have simply not been listening in the right ways, at the right frequencies for long enough to detect them. Our radio telescope searches for extraterrestrial intelligence. Under the banner of SETI, the search for extraterrestrial intelligence, have covered a genuinely tiny fraction of the candidate parameter space, a small number of stars across a limited range of frequencies for a relatively short duration. The absence of a detection under those conditions tells us very little. The second answer is more interesting and connects to a deep puzzle in evolutionary biology. Complex intelligence, the kind that produces language, tools, abstract reasoning and technology, did not appear on Earth at the first moment it was physically possible. Life emerged approximately 3.8 billion years ago. For roughly 3 billion years, it remained microbial. The transition to complex multicellular life occurred approximately 600 million years ago. Language-capable hominids appeared within the last few million years, technological civilization within the last 10,000. Each of these transitions appears, from the fossil record and molecular phylogenetics, to have been contingent on specific circumstances that were not inevitable. The endosymbiotic event that produced the eukaryotic cell, the cell type from which all complex life is built, occurred once in Earth's history. It was a singular, improbable event. The Cambrian explosion, the rapid diversification of complex animal body plans approximately 541 million years ago, was triggered by specific ecological and atmospheric conditions that may not have been inevitable. The mass extinction events that periodically reset evolutionary trajectories, most famously the end Cretaceous impact 66 million years ago, were catastrophic accidents that redirected the evolutionary trajectory of life on Earth in ways that made the eventual emergence of mammals and primates possible. What if intelligence requires not just time and a hospitable environment, but a specific sequence of catastrophes, contingencies, and evolutionary accidents that are genuinely rare? What if the path from simple chemistry to technological civilization is not a smooth gradient that any sufficiently old, sufficiently hospitable world will inevitably climb, but a gauntlet of improbable transitions, each of which must be navigated successfully? This is the core of what evolutionary biologist John Maynard Smith and biochemist Urs Sathmary called the major transitions in evolution, the handful of revolutionary reorganizations of biological information processing that mark the key steps from simple chemistry to complex civilization. Each transition appears to have been improbable. Each one seems to have required a specific combination of circumstances that did not necessarily recur. If this view is correct, then superhabitable worlds might be richer in life without being richer in intelligence. The biosphere of a warm, shallow sea world orbiting a K-type star for 8 billion years might be extraordinarily rich, diverse, complex, ecologically intricate, without having produced anything capable of building a radio telescope or asking the kind of questions we're asking right now. This leads to the third answer, and it is the one that makes astronomers most uncomfortable when they articulate it fully. We may be on Earth because Earth, despite its non-optimal characteristics by the superhabitability criteria, has the specific combination of features that made our particular kind of intelligence possible. Not the most common form of complex life, not the most ecologically dominant form, but the specific improbable form that asks about its own origins, builds instruments to measure the cosmos, and discovers other worlds. Our large moon, widely credited with stabilizing Earth's axial tilt and thereby maintaining relatively stable long-term climate patterns, may have been essential for the persistence of the land environments in which primate intelligence developed. Our position in the outer regions of the Milky Way, away from the crowded, radiation-intense galactic center, provides a relatively benign cosmic environment. Jupiter's gravitational presence has, over billions of years, shepherded the trajectory of potential impactors, reducing the bombardment rate in the inner solar system below what it would otherwise have been. None of these factors appear in the standard superhabitability criteria. They are harder to quantify, harder to detect remotely, but they may be as important as planetary mass or stellar type in determining whether a particular kind of intelligence, specifically the kind that asks these questions, can emerge. What does this mean for the 24 superhabitable candidates in Kepler's catalogue? It means they are fascinating. It means they are, by the best quantitative measures we can apply, more likely than Earth to host life. It means they may host richer biospheres, more diverse ecosystems, more persistent biological networks than our own world. But it does not necessarily mean they host intelligence. That question remains genuinely open, and genuinely open questions in science are not frustrating. They are opportunities. The next generation of exoplanet characterization, JWST's atmospheric spectroscopy, the forthcoming ground-based extremely large telescope, and its mid-infrared imaging capabilities, the proposed large ultraviolet optical infrared surveyor known as LUVOIR, the Habitable Worlds Observatory concept currently in development at NASA, will begin providing the data needed to distinguish between rich, sterile biospheres and biospheres that have modified their atmospheres in detectable ways. Biosignatures, chemical fingerprints of biological activity, include atmospheric oxygen, ozone, methane in disequilibrium with oxygen, nitrous oxide, and potentially more exotic compounds depending on the specific biochemistry involved. A planet whose atmosphere contains oxygen and methane simultaneously, two compounds that react rapidly with each other and would therefore not both persist in a purely abiotic atmosphere, would be a candidate biosignature world. Not proof of life, but a powerful signal. The first world in the Kepler superhabitable candidate list to produce a compelling atmospheric biosignature will be the most important scientific discovery in human history. Not an exaggeration. Not a rhetorical flourish. A factual statement about the stakes involved. And we will likely have that answer, or something approaching it, within the next 2 to 3 decades. The instruments being built now or planned now are capable of providing it. The question is not whether we can detect biosignatures on nearby rocky planets in habitable zones. The question is what we will find when we look. Let us pause here and consider something that is rarely articulated explicitly in these discussions. If we find biosignatures on a superhabitable world, say, on Kepler 442b, or on a similar world identified by a future mission, the immediate scientific conclusion is that life has emerged independently on a second world. That life is not a singular cosmic accident, but a general phenomenon. That the chemistry of biology, given appropriate conditions and sufficient time, is a tendency rather than a fluke. That conclusion alone would transform every domain of human thought: philosophy, theology, the psychological experience of what it means to be alive, the political and cultural frameworks by which human societies organize themselves and assign value, the long arc of scientific inquiry that runs from Copernicus removing Earth from the center of the solar system, through Darwin placing humanity within the continuity of all living things, to the recognition that Earth itself is not unique among habitable worlds. That arc reaches a new and profound point when the universe answers our question about whether we are alone, and the answer, if the superhabitable worlds of Kepler's catalogue are what the evidence suggests they are, is almost certainly no, not alone, just early. We began with a claim that sounded provocative, that Earth is not the best planet in the universe, having followed the evidence from Kepler's launch in 2009, through its 9 years of staring at a single patch of sky, through the thousands of worlds it found, and the 24 superhabitable candidates that emerged from its data, through the physics of stellar types and planetary masses and evolutionary timescales. It no longer sounds provocative. It sounds like a description of reality. Earth is remarkable. Let there be no ambiguity on that point. It produced life. It sustained it for nearly 4 billion years. It allowed the emergence of complexity, intelligence, language, science, and the ability to ask questions about the rest of the cosmos. These are extraordinary accomplishments for a middling-mass rocky planet orbiting a G-type star in the outer spiral arm of an unremarkable galaxy. But remarkable is not optimal, and the universe, vast, ancient, indifferent to our intuitions about our own centrality, has built worlds that score higher on the criteria that matter for life. Worlds that run warmer, weigh more, orbit more stable stars, and have had more time. Worlds that may, at this moment, host biospheres of a richness and complexity that ours has not yet achieved. Kepler found those worlds. It gave us their transit signals, their orbital periods, their estimated sizes, enough to identify them as candidates, to begin the work of understanding what they are and what they harbour. It gave us a map, not complete, not detailed, but real. JWST is now studying that map. Future missions will study it further. The story that began with Kepler staring at Cygnus is nowhere near its ending. One thread remains unresolved, and it is the most important one. We do not know whether any of the 24 superhabitable candidates host life. We have no atmospheric data for most of them. We have biosignature constraints for none. The question of whether better worlds than Earth are also inhabited worlds, whether the universe's superior habitats are occupied, is an open empirical question. Open, but not unanswerable. The instruments being built right now will reach toward that answer, and when they find it, when the spectral signature of an inhabited atmosphere appears in the data of a world older and larger and warmer than our own, orbiting a K-type star 1,000 light-years away, the implications will ripple outward through every conversation humanity has ever had about its own significance. We are not the centre of the solar system. We are not biologically unique in the tree of life. We are not the only potentially habitable world in the galaxy. And we may not be the best one either. As we continue to reach outward, with better telescopes, sharper instruments, and questions refined by each new discovery, the universe keeps answering, slowly, indirectly, but clearly. We are listening.